This is going to be kinematics, though you have had one lecture for kinematics at the board level already, but this is going to be a slightly different way of approaching kinematics from a more analytical point of view, with the use of calculus also, because now we are going to discuss kinematics from the point of view of the JEE syllabus and the JEE type of questions. Okay, so let's begin. Okay, so as I've already told you in that board lecture, the meaning of the term kinematics is that it's a study of, or it's, you can say, it's a study of the physics of motion. So basically, we in this what we do is we define certain parameters, okay, or physical quantities to describe the motion. And then develop the relationships between these. So those are called the equations of motion. So this whole chapter and this whole part of physics is about the equations of motion. And it does not deal with the cause of motion, which is force, which you have got into in the other chapter, which is Newton's laws of motion. Now, mind you, here we will be talking about, in this section, we will be talking about what is called particle kinematics.
So,
yes.
So I just wanted to ask one thing, that can we continue in that same book of the
Can
board?
Sorry, can we?
Can we continue in the same book only for that which we made for board lecture?
Yeah, you can, but ideally, what you should do is you should have a separate notebook for your board work, because you should do the board level questions from like, you are in which board, CBSE or ISC?
Sir, HSC.
You are in HSC, na? So then you should do a which college you are enrolled to?
Sir, TP Bhattacharya.
Achha, okay, right, TP Bhattacharya. So you should have definitely a separate notebook na, for doing the assignments and all for your board lectures.
Okay, sir.
Which is going to be from your, so you should have a separate notebook ideally. Okay?
Got it.
Yeah. So in this section of kinematics, we study what is called particle kinematics. Okay. Which means that, so let me explain this, or let me elaborate on this a little bit. So what we mean by particle kinematics here is that, okay, either we are studying the motion of a particle itself, and a particle is nothing but a point mass. So it is something very abstract in that sense, you can say. Okay. Or more accurately, we can say that, or the motion of a body, okay, that is basically a rigid body or an object, okay, but such that the moving object can be treated like a particle. As far as its motion is concerned. Now, one might think, how can we treat a rigid body or an object like a particle? But it can be treated like a particle because it is not rotating or spinning. So hence, it is moving in what is called pure translational motion. So there are a few technical terms over here. So it's moving in pure translational motion, okay, which implies that there is no rotation or spinning, and every particle within the rigid body has identical motion. So I'll explain this point also. First, just go through the explanation that I've given here. So I'll just zoom out a little. You can go through it section by section first. Okay. So even though we are calling this chapter kinematics, but essentially what we are studying here is called particle kinematics. We'll also be studying the kinematics for rigid bodies which are rotating, but that will happen a little bit later, at a later stage in a chapter called rotational mechanics. Okay. So in this chapter, what we have to keep in mind is that the equations that we are going to write are going to be the equations of motion for a particle. Okay. Of course, that doesn't mean that we are always only talking about a particle like an electron or a proton or something like that. We can be talking about the motion of a very large object like even a planet, but it should be moving in such a way that it can be treated like a particle. Now, when can we treat an object or a rigid body as a particle as far as its motion is concerned? Okay, we will discuss about that in more detail later. So I'm coming to that point. So there is a certain condition in which we may treat the an object just like a particle as far as its motion is concerned. And of course, there might be a situation in which we cannot treat it like a particle. So in this section, we are only dealing with those situations where we can treat an object or a body or whatever which is moving like a particle as far as its motion is concerned.
So,
Yes.
so what if the particle is in the state of rest?
Then it's not moving basically. But again, state of rest is with respect to a certain reference frame. So it is always relative. Understanding now? If we say
Yes.
an object is at rest on the surface of the earth, it's fine. With respect to the ground frame, what we call, which is the surface of the earth, it's at rest. But then somebody else is observing it from some other reference frame, like outer space or from another planet or from an orbiting satellite or something like that. Then it's no longer at rest. So everything is relative as far as kinematics is concerned.
So, sir, like if two people are sitting in the same car, so both of them are in the state of rest with respect to each
With
other.
respect to each other. That's true. That's
So
true.
for
And
that
specifically,
point of
we will
time,
say that in the frame of the car, they are at rest. Okay. In the frame of the car or in each other's frame, they are at rest. That's true.
okay, sir.
Sir, what is written there that moving object can be treated?
Yeah. Yeah. Okay. So moving object can be treated like a particle because it is not rotating/spinning. Okay. Hence, it is moving in what is called pure translational motion. So what does pure translational motion mean? So I've just written down a definition here, but I will elaborate on that. Okay. So what I'm trying to say here is that in this chapter, which is basically particle kinematics, we may be studying the motion of an object also, need not be a particle always. It can be an object, it can be a vehicle or whatever, but it should be moving in such a way that we are able to treat it like a particle. So when will that happen? When the motion is what we call technically the pure translational motion. When an object or a rigid body is moving in what is called pure translational motion, then it can be treated like a particle to study its motion. And that is because pure translation implies that there is no rotation or spinning, and therefore every particle within the rigid body has identical motion. So if every particle has identical motion, we don't need to write separate equations for every particle. We can just write equations for any imaginary point within the rigid body, like for example, its center of mass, and we can treat the entire body like an equivalent particle located at its center of mass. Okay. So just understand the keywords over here, and then I'll explain with an example or two, and it will become clear. Okay, this whole thing. Okay, so let me explain this point. Okay.
Sir,
Yeah,
sir, here we are told that equation of motion means equation will be formed.
yeah, we'll come to that. Like for example, those equations you've seen, b is equal to u plus at. That's an example of an equation of motion. Like that day
But
we
sir,
were. Yeah.
sir, if a person is at the state of rest for
Hmm.
one such thing, like if the person is sitting in the bus and another
Hmm.
person is also sitting in the bus, so with
Hmm.
respect to that person, he is in state of rest. But if a
Yes.
person is standing outside on the road, so
Uh,
with respect to him, the person is moving, so will the
yes.
equation be formed?
Yeah, the equations will always change. So whatever equations we write are with respect to a reference frame. So with respect to some other reference frame, the equations will change. And that part of kinematics is in fact it's a subsection of kinematics called relative motion. Okay, it's a very important part of kinematics and how we can transform the equations that you got in one frame to an equation in another frame.
Okay, sir, got it.
Like for example, if you are sitting in a car and another car is overtaking you, then you see it moving slightly slower than it's actually moving, no? Because you're yourself also moving.
Yeah, sir.
So the equation that you're writing for the velocity, displacement, and all that in your frame will be different to, like, let's say you are sitting in a car and a bus is overtaking you. So what you will write for the bus sitting inside the car will be different from the equations that somebody else who's at rest on the road outside will write, right?
Yes, sir.
So we will study how to transform one set of equations to another set of equations, okay, using the principle of relative motion. That is going to be the uh, a later part of kinematics when we come to that, okay, after learning how to write the basic equations. Okay. Now let me explain this point of translation to you a little bit. Okay. So now see, I'm taking an example of rigid body. Like one of you has sent me the message. I just forget who. That rigid body is what? Rigid body is basically a collection of particles which has a fixed shape and size. That means within the collection of particles, okay, the particles are connected to each other rigidly in such a way that the shape and structure and size cannot change unless, of course, you physically break it or something. So we're not getting into that. So this is a rigid body. But for example, a glass of water, the water in it is a non-rigid body because it's fluid in nature. Okay, or a very elastic material like a soft rubber object. It is not going to be a rigid body because even while moving, it might be stretching, compressing, and all that. So that's the difference between rigid body and non-rigid body. Okay. Now, as far as motion of rigid body is concerned, see, there are many different types of motion possible. Like this might be moving like this, in which case it's more or less doing a straight line motion. Okay, so if it's moving like, let's say on a straight surface, it's moving like this, then every particle within this is doing straight line motion. So there's no point writing equations of motion for every other particle. You can just write the equations of motion for the center of the body, and that represents the entire body. So that's the simplest case, no? Rigid body in straight line motion. Now another case could be that the rigid body is not moving in straight line, but it's moving in this way. It's moving like this. You can see. So the way I'm moving it, you can probably understand right now that every particle within the rigid body is having the identical displacement, velocity, acceleration, identical kind of path also. It's like that. So this is what we call pure translation. Okay, so pure translation means there is no rotation involved. So every particle within the rigid body is having identical motion. But then there could also be a motion like this. For example, like the motion of a pendulum, okay, or the motion of the blade of a fan, that it's rotating about a fixed axis. So the moment there is rotation involved, see what is happening. Every particle within the body is not describing the same motion. Like in this case, you can see that this particle, which is at this corner, or actually this one, which is at this corner, this will have the longest radius while it's moving. So it will cover the most distance. Compared to that, another particle which is here, that will hardly be covering that much distance. It will be covering a lot less distance. So all the particles are not having identical motion. So when this happens, we say it is pure rotation because it is rotation about a fixed axis. So I fix the axis, and with respect to that, all the particles are doing circular motion, or they are in a rotational path. Okay. So that's another type of motion. Now, yet another type of motion is what is called the general rigid body motion, which is the most complex form, which is also the most common form for a rigid body. If you throw an object, how you'll see it moving? You'll see it moving like this. Neither is it rotating about a fixed axis, nor is it translating, because if it was translating, it should have been doing this. It should not have been spinning. So this is what we call a combination of rotation and translation. That is about its own center of mass, it's rotating. But while it's rotating about its center of mass, the center of mass itself is traveling. Okay, so that is called the general rigid body motion, and we say that is a combination of rotation and translation. So that is the most complex type of motion. And that is what we'll come to in the end of our study of mechanics, which is the chapter of rotational mechanics. So again, coming back to what is relevant for us here today in this chapter is that we are not going to be dealing in this chapter with anything where there is rotation involved. Neither the case of rotation about a fixed axis, nor the case of rotation plus translation. We are only going to be talking about pure translation. So pure translation basically means no rotation. Okay, there is no axis about which it is rotating, neither a fixed axis nor a moving axis. The body is moving in such a way that every particle within the body has an identical motion. It's not spinning, it's not rotating. So the moment that happens, okay, we can describe its motion by just writing the equations for any particle within the rigid body. Or by default, you can think of the center of mass of the rigid body like the equivalent particle. So just write the equations for the center of mass, how they're moving, and that represents the motion of the entire body. So that is what is called particle kinematics, or a more technical term for it is pure translational motion. Okay. So in this particular chapter, we are studying particle kinematics. Okay. Or kinematics of pure translation, okay, of a rigid body. And once again, what we mean by pure translation of a rigid body means that there is no rotation involved. Hence, we can treat the entire rigid body as a single particle. Okay, so that's just one general idea that we should have before we get into the technical aspects. And you might, if you read some reference books and things, you might come across this term translation. So you must know what is the meaning of translation. The meaning of translation is this, that there is no rotation involved. So that means every particle within the given rigid body is having identical motion. That is, at any instant, it's having the same displacement, the same velocity, the same acceleration as any other particle. So when in pure translation, okay, a rigid body, or you can say a rigid body's motion is such that every particle within it is moving identically. That is, they have identical displacement, velocity, and acceleration. Okay. These are some of the key parameters, and we'll be studying these definitions in detail. So these are some of the key parameters that we use to describe motion: displacement, velocity, and acceleration. There are more parameters also, like distance, speed, and we'll talk about those also. But first and foremost, okay. So that is the definition of pure translation. Okay. And in this chapter, we are only dealing with those situations where a rigid body is in pure translation. So that's the background that you should know. That's all, nothing else. Okay. So once you understood this, now we come down to the different definitions of what we call the kinematics parameters. Okay.
Sir, can you please go ahead with that?
Yeah, let's go back. You don't need to write down this entire part in detail because I'll be sending you the notes. Just the keywords, and make sure you understand what we discussed over here. Okay? If there's any doubt, please let me know. I'll explain it to you then. Okay, so this is clear now.
Yes, sir.
Okay. Right. So now the first parameter that we'll talk about, or the first definition you can say of a physical quantity, is position. And now I want to initially talk a little bit generally about all these parameters. So we are not restricting ourselves to one-dimensional motion or straight line motion or anything like that. We're going to come up with the general definition. So even before we start talking about motion, okay, and equations of motion and all that, we should be able to define what is the position of an object, and we should be able to write some kind of a mathematical expression that represents the position. Okay, so that is where the vector analysis comes in for us. Okay, so position from now on, okay, is not going to be defined by coordinates, but it's going to be defined as a vector quantity. So sometimes we also call it position vector, and it is denoted typically with the symbol R. Okay, so when you see the symbol R related to kinematics, it typically means position. So the position vector R for a particle, let's say I'm calling the particle P, is defined as the vector joining the origin of the coordinate frame. So the coordinate frame is also called the reference frame. With the particle. So the position is nothing but a vector that represents, or the vector that joins the origin of our reference frame with respect to where the particle P is located. That's how we define the position as a vector quantity for a given particle. So if this is a standard Cartesian or rectangular coordinate frame we have defined, X, Y, Z kind of system. Okay. And now we have a particle that is located somewhere over here. So logically one would think that, okay, if I know the coordinates of the particle, that is as good as knowing the position, and that's correct also. Okay. But now we want to make a better definition of the position without using coordinates, but by using vectors. So instead of representing the position as the XYZ coordinate, what we'll do is we'll represent the position of that particle P with a vector that joins our origin with that point. Okay. So try to visualize this as a three-dimensional diagram, okay, where the origin like might be one of the corners that your room is you're sitting in, the room that you're sitting in, and the XYZ axis are three of the edges, like the edges between the floor and the walls, or between two walls and all that. So it's a three-dimensional space inside the room. So wherever a particle is located, now the vector joining the corner of the room that you've taken as the origin with that particle is nothing but its position vector. So if the coordinates of the particles are XYZ, or a particle at XYZ, okay, the position vector will simply be defined as xi cap plus yj cap plus zk cap. Okay. So this is how we convert coordinates into vector in case of position vector. So, and as you can see, the magnitude of that position vector will be given by root of x square plus y square plus z square. Okay. R is expressed in meters because it has the dimension of length. Okay. Meters is the SI unit. Centimeters is the CGS unit. Or it can also be expressed in kilometers, miles, feet, inches, so many other units. Okay. But typically here we will always stick to the SI unit system in our numerical calculations. Okay. So whether you're talking about the individual components XYZ or the magnitude of R or whatever, it has to be expressed in the unit of length. So now, just a little while back, we were talking about, rest and motion. When we can say an object is at rest, when we can say an object is in motion. In terms of position vector, it's very easy to understand that if my particle is such that its position vector is not changing with respect to time, is x is constant, y is constant, z is constant, then we'll say that in that reference frame, okay, in the reference frame of this xyz system, that particle is defined to be at rest. Whereas the moment the particle is behaving in such a way that the position vector is changing, it's not constant, then we can say that the particle is in motion. So that is the difference between motion and rest in terms of technical definition. If R is constant, it's not changing with time, then the state of kinematics for that particle is that it's at rest, it's not in motion. Whereas if it is changing with time, then we can say that it's not at rest, it's in motion. So you can just think of a reference frame as a system of axes, a system of XYZ coordinate axis, rectangular Cartesian coordinate axis, which is used as a reference to measure motion.
So if the particle P is in rest, then kinematics won't be applied.
We'll say that its state is that it's not in motion only. So that's about it. The only thing you'll say that, okay, kinematics wise, it will not have any displacement, it will not have any velocity, it will not have any acceleration. So all those parameters will become zero. And the first parameter that we're talking about over here, R, the position vector, that will be constant. It will not be changing. Apart from that, there's nothing special about it, right?
Yes.
Okay, now having defined position, now we come to the first very interesting parameter, which is displacement. And you will see that how the vector analysis makes the definition of displacement much more simple, but at the same time much more technical. Yes?
So can you scroll it up for a second?
Yeah.
Yes, sir. Done.
Okay. Okay, so the meaning of the term displacement is something that we are all familiar with. Okay. It is the one way of saying is that it's the shortest path from the initial to final position. Another way of expressing is that it's a straight line joining the initial and final position. But now that we have learned vectors along with calculus, we will go with a more technical definition that for a particle, or for that matter body, in motion, so that already we understand what that means. Its position is changing with respect to time. So for such a body which is in motion, the displacement, which is also a vector quantity, typically denoted with the symbol s. Okay, so the displacement s in a certain time interval is defined as the vector from its initial position to its final position. Okay. So this captures that spirit of the definition that you've seen before, that is the shortest path or the straight line or whatever, but now it's defined as a vector. And of course, this also means that the displacement is independent of the path. because the path might be more complicated. It might not be a straight line path. It does not depend on what path the object is taking. So let's understand this with a visual diagram. Okay, and then we will see that we have an even simpler definition of displacement if we use vector algebra. Instead of using words, if we use vector algebra, mathematics of vector algebra, you'll see that it becomes an extremely simple definition. Okay. So let us say what is happening here is that the particle was located at this point at time t equal to t1. It is located at some x1, y1, z1. So we will call this position of the particle as the position vector r1. Okay. So this is where the particle started with. Okay. Started from now. Okay. Now let us say that because it's in moving, it's in a state of motion. So let's say it's taking a very generic kind of path. So it might be going through a complicated path like this. And after some time, it is now located here. At time t equal to t2, it's at this position, which in terms of coordinates are given by this. So this new position at t2 in terms of a vector will be given by this vector. The vector joining the same origin, but with the new position of the particle r2. So during this time t1 to t2, so here I'm assuming that t2 is greater than t1. Okay, so in the time interval t equal to t1 to t equal to t2, okay, as the particle has moved from position r1 to position r2, its displacement. Now you apply the above definition of displacement and first understand in the diagram which is the displacement going to be. The displacement is going to be the vector that joins the initial position with the final position. So this is going to be the displacement. Okay. And now you think of your vector algebra, that what is the relationship between these three vectors, r1, r2, and s. Can you see there's some relationship between them? Can you tell me what that relationship is?
R1 plus S is R2.
R1 plus S is equal to R2, or we can say in other words that S is equal to R2 minus
R1.
Okay. So now you see this simple formula. No? This captures the entire definition actually. It's become very simple. This whole statement is captured by this simple formula that we can simply say that the displacement is delta R. It is the change in position. Okay, so displacement vector is equal to the change in the position vector for the given time interval. So this becomes now our, like, you can say a proper technical definition of displacement, that it is the change in position vector delta R. Okay. So I'll just take you through this step by step once more. So the word definition of displacement is what you're familiar with from before, that for a particle which is moving, the displacement in a certain time interval is defined as the vector which joins its initial position with its final position. Okay, so you can further elaborate and say that it's the straight line or the shortest path from initial to final or whatever. But now you can see that in terms of vector algebra, what this definition now means, this definition means this, what we can see in the diagram. That let's say the particle moved from this position x1, y1, z1 to this position x2, y2, z2 through this complicated path. So in between, I have also made this dotted curve kind of thing. This is representing the path of the particle. But you can see that the displacement does not depend on the path. It only depends on the shortest path possible from initial to final, or the vector joining the initial to final position. So that is this vector S. And you can clearly see S is R2 minus R1 because I've drawn R1 and R2 from the common origin, and S is like the diagonal of that parallelogram that is from head to head of one vector to another vector. So it's the difference. So in terms of vector algebra, what is S working out to be? It is working out to be R2 minus R1, where R2 is the final position and R1 is the initial position. So we can say it is the change in position. It's final minus initial position. Okay. So from this point onwards, whenever we think of the term displacement, we just think in terms of this vector equation, that S is equal to R2 vector minus R1 vector, or final R vector minus initial R vector, or simply delta R. And it captures everything that we need to know about the displacement concept. Okay. So just make a note of this, we'll discuss. Now the next thing we'll define.
Sir, can you please show the last line?
Yeah.
Okay, sir.
Now the next parameter we'll define is another vector parameter, velocity. So velocity is simply defined as the rate of displacement with respect to time. So now, because in calculus you have seen that there are two types of rate of change. And there is instantaneous rate of change and average rate of change. So accordingly, there are two types of velocity. Okay. So there is instantaneous velocity. Okay. Or by default, it is simply called velocity. So when we just use the term velocity alone, we generally mean instantaneous velocity. So that is defined as ds by dt, or instantaneous rate of change of displacement with respect to time.
Sir,
Yeah.
so for this instantaneous velocity, we have to apply differentiation on each component separately, right? Not the
Yes,
whole.
yes. I'll come to that also, how we use differentiation in a vector. Okay, we'll discuss about that also. So generally, if the vector is expressed in the component form, in the I cap j cap form, then you can just use the normal differentiation on each of the components and treat I cap, j cap, and k cap like constants. So accordingly, it has three components. Okay. Now, one thing important to understand here, that in a small time dt, okay, the displacement ds is equal to the change in position. So therefore, V, which we are writing as ds by dt, is one and the same thing as dr by dt. So you'll understand this if you think of it visually. Like now, just for convenience, I'm making a two-dimensional reference frame. So in this reference frame, like let's say at some time t, my particle was located here. Okay, so it's at this position vector. Okay, R. Now a very short time later, it's moved somewhere else. Let's say it's come here at t plus dt. Okay. So during this very small interval of time, what is the displacement vector? The displacement vector is nothing but the displacement is this now. Of a struggle. So this is that small displacement ds that is making during that time. But that small displacement ds is also equal to the change in position. Because now this is your new position at time t plus dt. Let's say we write this as R2. We write this as R1. Okay. So you can see vector, or in terms of diagram, what we mean by the statement that I've made here. That during a small time interval dt, this displacement ds is the same thing as the change in position dr. So v, which is written as ds by dt, can also be written as dr by dt, or velocity is equal to instantaneous rate of change of position with respect to time. Where, yeah, the symbol d by dt over here does mean differentiation with respect to time. So how do we calculate the instantaneous rate of change? If we know s or we know r as a function of time, we have to use the differentiation operation the way we've learned it before. So with examples, I'll explain how that is done with vector quantities. But this is the definition as far as instantaneous velocity is concerned. So during this very small time dt, the instantaneous velocity is that very small displacement ds divided by that very small interval of time dt. So ds being the same thing as dr, we can also say it is dr by dt. Okay, now let's talk about the second type of velocity, which is the average velocity. So average velocity is not defined at an instant, it is defined for an interval of time. So it is the total displacement during that time divided by the time interval. So we generally use the different symbol for average velocity to specify that we are talking about average velocity. Whereas when we just use v or we just use the term velocity alone, by default, it means that we're talking about instantaneous velocity. So the average velocity is S total displacement divided by the time interval. Or we can write this as delta R by delta T. Or that's the same thing as R2 minus R1 divided by T2 minus T1 for a time interval delta T equal to T1 to T2. So basically average velocity is what? It is the average rate of change of position with respect to time. Okay, or you can say it is the displacement in a certain time interval divided by the time interval. Okay, so very straightforward definition over here. So this does not involve any calculus. This just is the total displacement divided by the total time. Okay, so needless to say, the dimension of velocity is length per unit time. Okay, and SI unit is meters per second. CGS unit is centimeters per second. Common units are like kilometers per hour, okay, miles per hour, etc. Okay. One thing that you should remember is that conversion 1 kilometer per hour is 5 by 18 meters per second, or 1 meter per second is equal to 18 by 5 kilometers per hour. So remember this while doing questions, because you might have to interchange the units. Okay, so let's look at our first numerical example problem. Suppose a particle P moves about on a two-dimensional plane, which we'll take as our XY plane, such that at an instant t equal to t, its position is at x equal to 3 plus 2t, y equal to, just a minute, yeah, so its x coordinate is given by this expression, its y coordinate is given by this expression, let's say. Okay. Where x and y are in meters and t is in seconds. First of all, calculate its displacement S and the magnitude of the displacement from t equal to 0 to t equal to 2 seconds. Then second, express its velocity v as a function of time. And third, find the value of its velocity vector and magnitude of velocity. And lastly, we have to find the average velocity from t equal to 0 to 2 seconds. Okay, so just go through the question, give it a thought, try to visualize the motion also a little bit. But when it comes to solving each of the parts, you have to just apply the definitions.
So can you scroll up a little more?
Okay, very good, Parv. Your first answer is correct. So I'll just give a hint for everybody else also over here. Continue working on whatever you're doing. Okay. So if at time t, the x coordinate is given by this, and the y coordinate is given by this, okay, then we can also say that the position vector is 3 plus 2t I cap, okay, plus 4 plus 2t square j. Okay. So this is now like the instantaneous position. Okay, as a function of time. So now you can start applying all these definitions. Okay. Displacement is change in position. Instantaneous velocity is rate of change of instantaneous position. Average velocity is average rate of change. Just apply these definitions with the given values and you'll be able to figure out things very easily. Yes, Muskan, that's correct. Anybody else worked it out? Okay, so let's finish this question now. So we want to find, first of all, that displacement from 0 to 2 seconds. So for the first part, you can see that at t equal to 0, suppose we write the position vector as r0 or r0 or whatever, you can just substitute the value of t as 0. So you can see it is 3 I cap plus 4 j cap. And at t equal to 2 seconds, just substitute the value of t as 2 in the expression. So let's write that as r2, because it's at 2 seconds. So you can see that it is 3 plus 4, right? So 7 I cap plus 4 plus 2 into 4, 8. So that's 12 j cap. So this is, the particle is going from here to here. So the displacement during this time, you can say 0 to 2. Displacement during this time is the position at 2 seconds minus the position at 0. So if we just find the vector difference of these two, so that is nothing but 7 minus 3, so that's 4 I cap plus 12 minus 4, so that's 8 j cap in meters. So this is the displacement for that given time interval for t equal to 0 to 2 seconds. So of course, the value of the displacement that we get depends on what time interval we are talking about. Okay? And if we are not given any time interval, then the question itself doesn't make sense, okay? Because displacement is defined for a given time interval. And the magnitude of this you can simply see is, so that is 4 root 5 meters. Leave the answer in that form only. So that's done. Okay, now comes the more technical definition of velocity, because that now involves rate of change. So second part, we want to find the expression of instantaneous velocity. So that is, write it as this. So now this is where you need to pay attention how we are going to apply differentiation on a vector quantity. So it's all the normal principles of differentiation, including the fact that I will treat I cap and j cap as two constants, okay, which are vectors. So when I take the differentiation operator inside this expression, I'm just going to use the distributive property, and we'll leave I cap and j cap alone because they're constants. Okay, so here we have to understand that I cap and j cap, they're constants. So when we operate, this will become differentiation of the x component of position, that is 3 plus 2t, the whole thing multiplied into I cap, plus differentiation applying to the y component of displacement or position, that's 4 plus 2t square, and that whole thing gets multiplied with j cap. Okay, so our instantaneous velocity as a function of time, now you can see that this is having a constant x component, but it's having a variable y component. So it is not a case of uniform velocity, it is a case of variable velocity. The velocity is changing with time. So in the next section, when we talk about acceleration, we will see that this is a case where the body is actually in acceleration because its velocity is changing with time. Anyhow, so this is the instantaneous velocity in meters per second as a function of time. Okay, so that brings us to the third part where we want to calculate the value of this velocity at a particular instant of time, or in this case, two particular instants of time. Initially at 0 and then again at 2 seconds. So that will be directly applying or substituting the value of time as 0 or 2 seconds in this expression. Okay, so this is a very critical step over here, how we differentiate a vector quantity. This differentiation operator applies to this and it applies to this, whereas these two are constants, so they are left alone. Okay, so moving on to the next part. Now we want to find the instantaneous velocity at the instant t equal to 0. So let's say that's v0. So just substitute the value of t as 0. So you can see it as 2 cap. Or the magnitude of that is 2 meters per second. Okay. Whereas at t equal to 2 seconds, just need to substitute t as 2 seconds in the expression for velocity here, this one. So it's becoming 2 cap plus as much as 8j cap. So the magnitude of the velocity at that moment is square root of 4 plus 64, square root of 68, which will be very close to 8 only, but okay. So very good, Muskan. So far your answers are all correct. Okay. I'm sure the last one is also correct. Just verify. So then we have to find the average velocity. So V average is defined as delta R by delta T, or the total displacement divided by the total time. Okay. Okay. So you've already found out the displacement above. Okay, this one. So you just substitute that here. You don't even need to do any extra work. This is in meters, this is in seconds. So this is our average velocity from 0 to 2 seconds, that interval of time. Okay, so very good. Hope this is fully clear to all of you. So now we move on to the last definition of among these vector parameters, and that is, as you might have guessed, acceleration.
Sir, can you please scroll up for just 1 minute? I actually
Yeah.
got disconnected in this.
Okay, okay, sure.
Yes, sir.
Okay, so now let's look at the definition of acceleration. In general, it is defined as the rate of change of velocity. It's a vector quantity. So again, we define two types of accelerations: instantaneous acceleration, that is the instantaneous rate of change of velocity with respect to time, and average acceleration. For that, we use the specific symbol. That is the average rate of change of velocity with respect to time. Once again, if we use just the term acceleration without any prefix, by default, we are talking about instantaneous acceleration and not average acceleration. Okay, so dimensionally, you can see that acceleration has the dimension of length per unit time square. Okay. So acceleration is expressed in meters per second square in SI unit system, or centimeters per second square in CGS system. And we can use all sorts of hybrid or non-standard units like kilometer per hour square or kilometers per minute square or whatever. Okay. Not really important. Okay, now having defined the vector parameters of position, displacement, velocity, acceleration. Again, two types of velocities, two types of acceleration, average and instantaneous. Okay. Now we come to the scalar parameters. And they are namely distance and speed. So because they are scalar as opposed to the above ones which are vector, they are not necessarily simpler to understand. In fact, they are a little bit more complex. Distance, which we might denote with the symbol small d, is the length of the path traveled. In a given time interval. So for example, if a particle is moving from here to here via this kind of a path, so this total path length that is my distance traveled. So it can, for example, happen in such a way that a particle comes back to where it started from. So in a round trip, okay, it may happen if the path is what we call a closed loop path. It may happen that displacement equals to 0, but distance is not equal to 0 in a time interval. And a very good example of that is completion of a circumference in a circular path. That's an example of something where, so in general, what will happen is the magnitude of displacement will always be less than equal to the distance. Okay. And the magnitude of displacement will be equal to the distance only if the body or particle, whatever, moves along a straight line, and that too without reversing its direction. Just that it's moving along a straight line is not enough, because something could move along a straight line, stop, and then come back along that same straight line. So it's still moving along a straight line, but there the distance would again be more than the magnitude of displacement, because the path length traveled is more. Okay. So this phenomena, that is magnitude of displacement, is identical or equal to distance. It is happening only if the body or particle moves along a straight line path in the same direction. It should not switch direction. So often people will in a hurry say that, okay, if the motion is along a straight line, distance is identical to displacement's magnitude, but that's not true. Okay. Straight line means that the path is along a given axis. It doesn't necessarily mean that the direction is not changing. It could be going in that positive direction and then coming back along the negative direction. Okay. That also constitutes motion along a straight line. But in that case, the distance will be more than the displacement. Okay. So magnitude of displacement is equal to the distance traveled only when it's that very special case of moving along a straight line without altering the direction. So that is the scalar parameter of distance. So there is no other formula for distance. It is something that has to be calculated from the geometry of a given path. For example, if it's a circular path and you know that it's covering a certain arc length, then you can calculate it using that angle and radius formula. If it's a full circumference, you know it is 2 pi r. Similarly, if it's moving along a rectangular, path with a perimeter known, so you can calculate the distance from that geometrical fact of how to. Or you can think of an experimental method of how to calculate the path length. You'll have to find some way of tracking the path of the given moving body. So if you're able to track it, like as it is moving, maybe it is spilling ink or it is leaving some tracks like tire tracks on the given surface or something, then you'll actually have to measure that path length, okay, using an inch tape or using a piece of thread and twisting it along the path exactly as the body is moved, and then later measuring the length of that rope or string or whatever. So those would be like the experimental ways of how to measure distance. So distance, though it's a scalar quantity as opposed to displacement, which is a vector quantity, actually distance is a little bit more complex compared to displacement. Displacement is very simple. It is R2 minus R1. So same goes for speed.
So,
Yeah.
so can you scroll it just for a second?
Yeah.
Yes, Smita.
So speed, it is defined as rate of distance traveled with respect to time. So again, there is that whole business of instantaneous speed. that is exactly actually magnitude of instantaneous velocity. Now, why this happens is it equals to the magnitude of the instantaneous velocity. Because in a small time, or in what is called a differential time, so the term differential time means this thing, that limit delta t is tending to 0, that calculus definition. Okay. So in a differential time dt, the distance traveled is equal to the magnitude of the displacement. Okay. So again, you have to understand this with visualization. Okay. That even if a body is moving in a very complex turning kind of path, constantly twisting and turning kind of path, but if you take a very small interval of time, which is called a differential interval, interval of time dt such that it's a change delta t small enough to tend to 0. So even if the path of the particle is very complex like this, but if you're talking about a very small interval of time, we're talking about a displacement during that small interval, that is this ds. Okay, so that will be equal to magnitude of ds only will be equal to the distance in time. So that is why this can be said. So that is why now we can see that the instantaneous speed is equal to magnitude of instantaneous velocity. Whereas now, before you note this down, you should understand the contrast to this also. So when we talk about average speed, it's not going to be the mod of average velocity. Average speed, it is equal to the average rate of change or average rate of distance traveled with respect to time. So that is equal to the total distance divided by the time interval. Now, the important thing is that the average speed is not generally equal to, it is less than, sorry, it is greater than equal to magnitude of average velocity. Why? Because the distance traveled in general is greater than equal to magnitude of the displacement. It's equal to only in a special case, which we have discussed earlier. Okay, so in general, this is greater than equal to mod of average velocity. Because distance d in general is greater than equal to magnitude of displacement. So once again, now if you're visualizing an object or a particle moving in whatever path, but over a broader range of time, so it's moving like this, or let's say it was here at time t, and now it's here at time t plus delta t. So you can see this line that I've drawn here, this is your magnitude of displacement, whereas this curved path from here to here, that is your distance. So you can see distance is greater than magnitude of displacement. So that means your average speed is greater than equal to the magnitude of average velocity. Again, equal to only in the special case of motion along a straight line where the direction is not changing. Okay. So just make a note of this definition of speed, both in terms of instantaneous and average, and more important in the definition to remember the fact that in general, instantaneous speed is always equal to the mod of instantaneous velocity. But average speed is generally speaking not equal to. It can be greater than, and only in a special case it can be equal to mod of average velocity. Okay, so hope this point is also understood. Okay. So this thing that I was saying, that the distance can be more than the magnitude of displacement. Therefore, the average speed can be more than the magnitude of average velocity. This can even happen along a straight line, as we've discussed. Okay, it could be that you go 2 kilometers towards north and then come back 1 kilometers towards south. So your total distance traveled is 3 kilometers, but your displacement's magnitude is only 1 kilometer. So your average speed is going to be 3 times as much as your average velocity's magnitude. Okay, so that's something to keep in mind. Now, what we will do is we will actually reduce all these definitions to the special case of motion along a straight line. And then we will come back later to motion in a two-dimensional plane and then eventually 3D motion. So the whole purpose was to be able to understand all these parameters in the most general form, the most correct definitions, which are the vector definitions. Then we will think of motion along a straight line as a special case of that general definition. Okay. So after having understood these definitions and the relationship between these quantities, now we come to the special case of motion along a straight line, which is a somewhat simpler version of motion. Okay. Or in short form now, we'll just call it 1D motion. Okay. Or one-dimensional motion. So that's how the term 1D comes. So we'll see that all the parameters, we will switch them from vector parameters, which is for the general definition, to scalar parameters, or actually it is still vectors, but we'll call it scalar notation. Okay, which is specifically for 1D motion. So it's not to say that, velocity in a 1D motion becomes a scalar quantity. It's still a vector quantity, but it can be represented in a scalar notation without using unit vectors. Okay? Because the direction is only two possible directions. So we just need algebraic sign. Okay? So here position was defined as R. Here position we will define as just a coordinate. So X. Okay. Assuming the x-axis is along the line of motion. So we have selected our x-axis along the line of motion. So we will represent the position at any instant as just the x coordinate. Similarly, we could have taken it as the y axis, so it would have been y coordinate or whatever. But basically now we don't need to represent the position by a vector quantity anymore, like xi cap or like yj cap. We can drop the unit vector because there's only one unit vector involved. The motion is only along one fixed axis. Okay. So like that, displacement was defined as change in position, or R2 minus R1. So now here displacement is defined as change in x coordinate, or x2 minus x1. And the important thing here is that displacement can have positive or negative sign. Algebraic sign becomes important depending on the direction. So displacement is still a vector quantity, but because it's a one-dimensional vector, we don't need the unit vector notation. We can use a scalar notation for it, where plus and minus sign will give us the direction. Similarly, instantaneous velocity was rate of change of position or rate of change of displacement. So here, velocity is just defined as this. So once again, velocity also can have positive or negative sign depending on the direction. Okay. And similarly, average velocity is s by delta t, or delta x by delta t. Instantaneous acceleration is dv by dt. Average acceleration is delta v by delta t. So all these vector notation quantities are reduced to scalar notation. Similarly, acceleration can also be positive or negative depending on the sign. So this is motion along a straight line. Okay, this is not motion along a straight line with uniform acceleration. We will come to that also. That is a specific further, I mean, that's a further specific case. Uniformly accelerated 1D motion. So there we can use those three equations we talked about in the board lecture, v equal to u plus at and the other two. But this is a more generic situation. The acceleration may be uniform, it may not be uniform. But the only thing that you're saying is that the motion is along a straight line. So it's one-dimensional motion. So the general definition and relationship between the parameters in one-dimensional motion is position is given by a single coordinate. Displacement is therefore the change in the coordinate. Velocity is the rate of change of that coordinate or position or displacement with respect to time. And acceleration is rate of change of velocity. Okay. So before we move further, you understand that these quantities are still vectors, but they have only two possible directions, plus and minus. Hence, we don't need to use the unit vector notation, just the algebraic sign is enough. Okay. Now, the other thing is that when we express the instantaneous acceleration as instantaneous rate of change of velocity with respect to time, we can also express it as second derivative of position or displacement, whichever we want to say, with respect to time. Therefore, instantaneous acceleration is also expressed as a second derivative. Okay, now the next thing is the application of calculus in one-dimensional motion. So next couple of lectures for now, we'll be concentrating on 1D motion before we come back to the general 2 or 3D type of motion. Okay. So instantaneous velocity is rate of change of displacement with respect to time. It means that displacement is integration of velocity with respect to time. Or in a certain time interval, let's say t equal to t1 to t equal to t2, okay, the displacement, which will be the change in the x coordinate, it will be equal to the integration of velocity with respect to time, t equal to t1, t equal to. So this becomes like a reversal of this definition. If v is rate of change of s, that means s has to be integration of time of v with respect to time. And likewise, E is equal to dv by dt. That means delta v is equal to integration of ed. Or in other words, in a certain time interval, if time interval t equal to t1 to t2, if the velocity changes from v1 to v2, okay, then the relationship between this we can say is that final velocity minus initial velocity will be integration of the acceleration with respect to time from the initial time t1 to the final time t2. So again, this is the application of definite integration. This and this you can see is the application of definite integration to calculate displacement in a specific time interval from t1 to t2, or change in velocity in a specific time interval from t1 to t2. So let's look at a particular example. So now what happens is that t equal to 0, a particle starts from x equal to 0 with an initial velocity of plus 20 meters per second along the x-axis. Now, if the particle has an acceleration which is basically variable with respect to time,